Well, good night, everyone, and welcome to this talk about how we productionize machine learning in InfoJobs. We will explain, well, my name is Isaac Fortun. I am data scientist in InfoJobs, and he's my colleague Juan Fernandez. He's a machine learning engineer. And together we will explain how we productionalize machine learning models in InfoJobs to increase the performance of the work done by the data scientists. First of all, a few words about Adevinta. Adevinta is an online company, company containing online marketplaces operating all over the world. For example, in Spain, we have some portals like Fotocasa and Maritaclia for real estate, Coches.net, Motos.net, Milanuncios, and also InfoJobs, where Pampa and I are working. Here you have some numbers about our revenues and also about the size of the company. But, well, let's talk about the actual talk. First of all, I will explain a bit the background of the project, why we decided to do this project that we will present today, and also the data science or machine learning theory and the project that we developed. Then Juanfra will explain how the machine learning engineering part of our team put our model into production. Okay, so let's start why we decided to do this project. And the main reason was that we wanted to attack some of the main user pains that we detected through UX surveys or other feedback platforms that we have in the company. And one of the main pains in InfoJobs, I don't know if you used InfoJobs in the past or you are using InfoJobs right now, but one of the main pains was that people were complaining about that they were not able to upload their own CV. Sometimes the users spend a lot of time creating their own CV in Word or in some platform, and then when they extract it to PDF, they want to upload it into InfoJobs, but this was not enabled in our platform. Why we didn't want the users to upload their own CV? Because we thought that if we let the users upload their own CV in InfoJobs, they could stop filling the CV in our platform. So we would end up having a lot of PDFs, but with unstructured data, and we would lose the structured data that currently we have in our platform and that we use to help the users to find better offers. For example, if we know that a candidate is a gardener, we can recommend them offers related to gardening. If we don't know this because we only have a PDF form in which there is a lot of text in there, but we cannot understand the text, we cannot help the users in this way. The second pain that was detected is that this process of updating the InfoJobs CV was quite long and complex. Again, users that have already worked in creating their own CV wanted to just upload their own CV and not fill again all the fields in the InfoJobs page. So our idea was, okay, first of all, we will let the users upload the CV in PDF. But then to avoid the losing the data of our users, what we decided was to create a machine learning model that is able to understand everything inside the PDF and automatically fill all the fields in the InfoJobs curriculum. This way, we are not losing data anymore because we have the PDF file, but moreover, we have all the fields correctly classified into the categories of the InfoJobs CV. Then we are not losing data, and also because this is automatic, the process is not long and complex anymore. It's quite faster. So we decided to go for it. And I will explain now which kind of machine learning algorithm we created for doing this kind of task. Well, the idea was to start with a PDF and then end up with like a JSON-like file in which all the information inside the document is automatically extracted and correctly classified. For example, the personal information of the person, a list of all the experiences that he has had in the past with all the companies, when they start, when they ended, etc. To do this, we created like a monster, this CV parsing model that it's like a monster with 3 legs. The first leg was a piece that took the binary PDF file and extracted the text, the raw text from it. There are a lot of libraries that already do this, but it was a bit tricky because sometimes people is quite creative when building their own CV. So sometimes they put columns or they put tables. So extracting the text in the correct order was quite a challenge and was the first piece of the model. The second part of the second leg is the actual machine learning model. In fact, this is a deep learning model. Later, I will explain a bit more about it. And this model, what it does is classify every word in the raw text and assigns a label to each word, telling, okay, the first word is the name of the person. The second word is the job title of the person. This word here is the company where they work. Then a number is the year in which they started their studies, etc. We have a list of words and a list of labels. And finally, the last leg of the monster is a post-processor that takes all these predictions, corrects it, and puts them in a structured form like this one here. At the end, we are using a technique called named entity recognition that does exactly this. Takes all the words and classifies them. To do this, we use 3 main Python libraries. First, PyTorch, because deep learning is at the end is working with tensors, with multidimensional tensors and multiplying them and working with them. PyTorch and also TensorFlow are two of the main libraries in Python that can help you in managing all these tensors. Then Hugging Face is another Python library that contains a lot of already created deep learning structures. For those who don't know the concept of deep learning is a kind of machine learning algorithm that consists on neural networks. These neural networks can have a lot of different forms and architectures, and Hugging Face is a library that contains a lot of these pre-created neural networks. And finally, we use BERT, that is a language model, a particular deep learning model that has been used widely in the last years. It's very powerful, so we base our model into BERT. We start with this pre-trained model and add the logic to solve our problem. And then just, I will not go in details about the actual architecture of the model because we think that this is out of the scope of this talk, but if you are interested, I can tell you more later. Just, I want to give you some idea about the impact of the solution that we built. Some numbers, for example, the pain that the people, the users of InfoJobs are complaining about not being able to upload their CV has disappeared from the top panes. Also, we are able to suggest information, even if someone has an InfoJobs CV, if they upload the PDF, we can tell them, okay, these experiences here are not in your InfoJobs CV, so maybe you can add them. So all these suggestions has 4 out of 10 users with uploaded CV, we have been able to suggest an improvement and grading of the CV. And of all the suggestions, 88% of the users who open them are satisfied, and 90% think that this is useful. And finally, we have seen that the users that upload their PDF are updating the InfoJobs CV more frequently than the ones that doesn't upload their PDF. So this is mainly the project, and the data science part of the team worked in building this model and designing the deep learning neural network and everything. And then we handled this model to the machine learning part of the team, and they were in charge of putting everything in production. So Juanfra will explain now how they did it.
Thank you, Didac. Well, I'm Juanfra, I'm the machine learning engineer. He's the data scientist. He does his black magic. He gives birth to his model, and then he handles it over to me and says, okay, put it in production. So the model is working, the performance is good, so the different PDFs are really well tagged. Right now, put it in somewhere and provide the service for the actual users of InfoJobs. So, what do we do? Which is the environment of InfoJobs? In InfoJobs, we have all our machines inside the AWS. So we are a cloud computing company. And the architecture that we use is this one. It is a Kubernetes cluster with a lot of nodes. And each node is shared. And inside each node, there are several pods that hold different applications. One of these applications will hold the model that Didac developed. Okay? And it's very important, this data, because the pods are limited, are not very big, in order to provide a really flexible holding of applications inside each of the nodes of the cluster, of the Kubernetes cluster. So it has 4 CPUs, 4 virtual CPUs, 4 gigs of memory, and nothing else. And here comes the problem. When we, for first time, put our model inside one of our pods, we started to see that it was slow. So we arrived to moments in which we had to wait for 82 seconds to parse a PDF and get the data structure back. This wasn't acceptable because we can't, so we can use it, but we can't use it in real time. So we will need to find a solution to productionize this model. The model is similarly big. Is, for you to know, it's about 1.5 million of neurons. So in 4 gigabytes of memory, it goes slow. It has not enough space. So we realized that our bird was able. So we have to get a solution for that. Well, to understand more the problem, we need to understand how is the architecture inside this Kubernetes cluster. So we have a PDF that goes to a Kafka, okay, a Kafka queue, and it's converted into an event. And then we have a typical microservice that gets these events and knows, gets the information about this is a PDF parsing. So this microservice works in less than 100 milliseconds, so this is not the problem. But it goes to the microservice that holds the model that the data scientist developed, and we found out that it was over 3 seconds. Over 3 seconds if the queues of this microservice were not full. So whenever the queue started to grow, it was 3 seconds, more 3 seconds, more 3 seconds more, and it arrived to the 82 seconds that we have seen before. So we have found out where the bottleneck is. So we had to ease this bottleneck and make it more performant. Okay, so we get we dove deep inside the microservice to see what was going on and which was the bottleneck. Okay, the microservice is the architecture of the microservice is the one that you see right now. Inside the Docker pod, there is a unicorn server, which provides the service of REST for the Flask application that is written in Python and holds the model inside. Okay, and the model itself, the application, the Flask application, is divided in these three parts. That is, you have already seen these parts because Didac has explained it. The PDF parsing was benchmarked only for a 65% of the computing time. The post-processing of the model was only a 34, but the model inference, the actual work of running the model and getting the target text was almost 50% of our time. So we have to attack this one. And what did we do? Well, apart from crying, okay, we got our phone and we called AWS support. We tell them we work a lot with AWS. We have a lot of AWS systems, so we have a very strong and close support. So we call them and we explain whatever I have just explained to you, and they told us, okay, you choose us because organizationally you are close together and because we have some solutions that we can discuss, okay? And they started to talk about in-house quantizing, trying to use GPUs, nodes, and a lot of other things that can help us. We started with the upper part of it. We tried to use another kind of processors or quantize the model, and we got some gains, but it didn't work. So we went deeper, and we asked the people in AWS, what other options do we have? The first one was going for beefier CPU instances. It didn't work. We tried to optimize the model. It didn't work. Then we went for GPU instances. It worked, but it was expensive. And then the people in AWS told us, but there is something new. We have a new processor. We have something that is called inferential processors that are processors of a specific purpose devoted to make inferential, to run the part of the model that is the prediction. So we started to explore this one, okay? And we make some benchmarks and we see, okay, CPUs are mostly useless, GPUs are really performant, they lower half of the times, but when we arrive to inferencia, we get 2 orders of magnitude improvement. So we were completely delighted, but we were afraid about the price of it because inferencia time is expensive. The thing is that we did a benchmark of costs, and the surprise was that even being expensive for time unit, as they were so fast, we used very few inferencia time, so our costs were lower. So it was the perfect solution. So we went for it. And to go for it, we have to devise an architecture that fits inside our company, and we devised this one. We kept our microservice, the microservice you already saw in the other slide, the one that is composed by Unicorn, Flask, and Python, but we have the model outside of the microservice. We put the model in what is called Amazon SageMaker endpoint, which runs inside a machine that has an inferential processor. So our microservice is computing mostly nothing and asks the model that is running in a machine that is very fast for the tagging process. And this improves a lot the process. Okay? And that's it. And what happens next? Well, what happens next for us is that we can provide real CV parsing. So whenever you sign in InfoJobs, you don't need to put your data by hand. You can just upload a PDF, and in real time, you will get the information in your PDF in a structured form. You can correct, fix whatever is not completely accurate, but you don't need to copy and paste all your information there. Okay, and this works nearly real time. We can go deeper in the models. If we find out that the model falls short for some tasks, we can make bigger models, even bigger than a couple of hundred of millions of neurons. And we can even leverage the real-time user feedback. Whenever you upload your CV and you get the tag CV with the structure and you fix whatever is not correct, we are getting for free and tagged example. Okay, and as you see, everything is an advantage in this scenario compared with the previous scenario that we had. And that's it. Here you have our social network links if you want to contact with us or make questions or whatever. And that's it.
Yeah, if you have any questions now.
I'm just curious about how far in this process are you? I mean, how long is it started?
How long ago it started? Well, we started with it. So to make the model, it was kind of.
We were about 9 months to 1 year to make the whole model, because we needed a lot of data to train the model. We needed to prepare a lot of data to develop the model. Then the model was finished about 1 year ago or one year and a half ago.
Yeah.
And currently they are working in this second part of making it fast.
Yeah. Yeah, we are almost done with the part of putting everything in SageMaker. We already have some prototypes that are working in SageMaker. In pre-production, we are going to production as fast. So all in all, kind of 1 year and a half or so.
Yeah.
Okay. Yeah, more or less.
Okay, so making the model already in production better has been like 1 year more or less.
So could you repeat the question?
Yes. The time you have spent making better the model.
Okay, improving the model, but this is data science.
No,
data science, or do you mean improving the performance, the speed of the model?
Yeah, because you could work in parallel at the same time, making better.
Kind of. At the beginning, data scientists are the ones that are working because there is nothing to test. But whenever they have some fairly good performance, they still try to make a better model in the sense of the prediction is better, and we get into it and start to try to productionalize, and we focus in the computational part. But they still work and retrain the models, and they provide the models to us whenever they are better than the ones that we already have. Okay. So we have some overlap. Okay.
Prediction training is
Yeah, correct.
and then you keep getting better the model.
Yeah, we try to get more data to improve the model, and also to find better architectures until, well, yes, forever, or until we are satisfied enough with our model and we can focus in another tool. Yeah. Yeah.
If you know that some users already have like the PDF and the data there, just like how people have that for people,
Yeah, I will try to summarize. the first thing that we did was to create like fake PDFs with the InfoJobs the data that we have in InfoJobs. We started mixing data from everyone and creating fake data, and with this, we trained a first model. This was working quite well, but not perfect. Then we started letting the users upload their PDF, and we had two persons that were tagging all the parts of the PDF and saying, what is this? And with this process that took maybe 6 months to have at the end like several thousands of labeled CDs, we improved a lot the performance of the model.
I think was that the synthetic training set was, we tried to randomize it a lot, but it was more uniform than the real data. Whenever the real data arrived, it improves a lot the way the model works.
This this inference processor.
Yeah.
What part did it run? Was it strictly the inference, or was it also the parsing and the post-processing?
No, well, the inference processors are only called while the inference is run.
In the middle leg of the
in the middle leg of the monster, in that part, and only if your model is explicitly compiled to use the processor. If not, you can run, because those instances have shown regular processors, and then this inferentia is kind of coprocessor, and you have to compile explicitly for it to get into. If not, you can run the model in the shells, but it's not as performant as if you compile it for the inference at the checksum. Okay, and only the model. The rest of it there is, because the process is not like, so when you have deep learning models, you are crunching vectors, and the architecture of inferentia is really performant with this kind of operations. When you are just parsing a PDF, can be a sequential, whatever it does, but it's not crunching vectors, so you get no improvement.
Okay, well, thank you.
Okay.
Should we move to the next?